A notebook is no longer just a device. It is the daily gateway to work. Through this device, people access email, specialist applications, meetings, documents, digital signatures, encrypted communication, sensitive information, and administrative decisions. When a notebook is engineered properly, the technology recedes into the background. The person opens the device, signs in, reads email, works on a document, joins a meeting, decrypts a message, signs a file, and opens a specialist application. The work flows quietly, reliably, without unnecessary friction. But this apparent simplicity is not accidental. It is the result of engineering. A good digital workplace is not created by procurement alone. It is not created by device management alone, and it is not created merely by developing a management tool. It is created by a controlled end-to-end chain. When notebooks are not engineered properly, the problem rarely appears as a single dramatic outage. It appears as a series of small frictions. A PIN prompt is delayed. A card reader does not respond immediately. A certificate is not available when the application expects it. Outlook does not reliably open an encrypted email. A driver behaves differently after an update. A network session reconnects. A user signs in twice. A support ticket is opened. Each incident may look minor. But in large organization, minor incidents are not minor. They scale. What is one lost minute for one person becomes a structural efficiency problem when it is repeated across tens of thousands of workplaces. Consider a conservative calculation. If 50,000 employees lose, on average, only 2 minutes per working day through small technical frictions, then over 220 working days, this amounts to more than 366,000 lost hours per year. That is roughly 45,000 working days, or more than 200 full-time working years. At 5 minutes per day, the figure rises to more than 916,000 hours per year. That is more than 114,000 working days, or more than 500 full-time working years. These figures are not a measurement. They show the order of magnitude. A delayed PIN prompt may be irritating for one person. At scale, it is a productivity issue. A recurring certificate problem may be a support case for one user. At scale, it is a platform quality issue. An update that repeatedly creates side effects is not simply bad luck. It is evidence that the platform is not under sufficient engineering control. In complex workplace environments, the most visible component is often mistaken for the cause of the problem. A delayed PIN prompt may appear to be a smart card issue. An encrypted email that does not open reliably may appear to be a smart card issue. A card reader that behaves differently after an update may appear to be a smart card issue. Sometimes that diagnosis is correct. But sometimes the smart card is simply the point at which a wider platform weakness becomes visible. The real issue may lie in the interaction between hardware, firmware, drivers, cryptographic providers, certificate propagation, Windows builds, Office integration, network conditions, security policies, update management, and support processes. In such cases, replacing the visible component does not necessarily solve the underlying engineering problem. It may simply move the friction elsewhere. The smart card is not the enemy. Nor is it automatically obsolete simply because it is physical. In government and public administration, a smart card can support a very appropriate security architecture. It can act as a separate physical trust anchor. It can separate private keys from the notebook. It can make certificates available under organizational control. It can combine strong authentication, digital signature, email decryption, and access to sensitive applications. That is more than a convenient or inconvenient sign-in method. It is a PKI-based security model. Anyone proposing to replace such an architecture must therefore do more than compare it with a modern sign-in mechanism. They must show how the full set of existing security functions will be replaced to an equivalent or better standard. Sign-in, application access, digital signature, decryption, privileged use, recovery, auditability, key lifecycle management, and organizational control. The technical documentation does not support a simple black and white conclusion. Microsoft continues to describe smart cards as tamper-resistant, portable security devices for tasks such as client authentication, domain sign-in, code signing, and securing email. Microsoft also describes Windows Hello for Business as a strong modern mechanism, a device-bound credential unlocked with a PIN or biometric gesture, typically protected by hardware and designed for phishing-resistant authentication. The conclusion is not Smart Card old, Windows Hello for Business new, therefore Smart Card out. The conclusion is there are different security models. With Windows Hello for Business, the trust anchor is more closely tied to the device and to the Windows and identity platform's integration. With a smart card, the trust anchor is on a separate physical medium that can also be used for PKI, signature, and decryption. The professional question is not which mechanism sounds more modern. The professional question is which security model better covers the requirements. Modern high-assurance architectures do not simply follow the line Smart Card out. In the United States, PIV and CAC cards remain central security instruments for government personnel, contractors, system access, digital signature, and encrypted communication. NIST continues to define PIV as a standardized, interoperable identity credential for federal employees and contractors. CAC cards contain PKI certificates used for digital signature, email encryption, and email decryption. At the same time, NIST has developed the architecture further. Phishing-resistant authentication, high assurance levels, non-exportable private keys, device signals, federation and derived credentials for situations in which a physical card is not practical. The lesson is not smart card or modern. The lesson is high assurance must be operated in a modern way. A smart card-based PKI architecture can remain entirely contemporary if it is well engineered, well integrated, and complemented where new form factors are genuinely useful. High security must not mean that everyday work repeatedly comes to a halt. A smart card architecture can be very secure, but it must be engineered properly. Card profiles, readers, mini drivers, middleware, certificate handling, Outlook, Windows cryptography, network behavior, security policies, updates, and support all have to function as one coherent chain. High assurance must not become high friction. If a sector solution is poorly integrated, usability suffers. But security suffers as well. Poor user guidance creates workarounds, support pressure, user error, and frustration. Good security requires good technology. And good technology requires end-to-end responsibility. A managed device is not yet a well-engineered workplace. An organization can inventory devices, distribute policies, deploy updates, and check compliance. All of that is necessary, but it is not sufficient. A workplace is well engineered only when people can work reliably. They must be able to sign in. They must be able to communicate. They must be able to sign and decrypt. They must be able to use specialist applications. They must be able to recover from failure. They must remain productive after updates. Endpoint engineering therefore does not mean we introduce a management tool and then problem is solved. Endpoint engineering means we take responsibility for the full working capability of the endpoint. That is the higher standard. And it is this standard that determines whether a large organization works efficiently or loses time every day through avoidable friction. Professional endpoint engineering begins before a device is rolled out. It begins with explicit requirements: security, usability, reliability, performance, maintainability, interoperability, recoverability, and sovereignty. Those requirements must then be translated into an architecture. Which hardware models are supported? Which firmware versions are approved? Which smart card readers are allowed? Which mini drivers are used? Which cryptographic providers are permitted? How are certificates issued, propagated, renewed, and revoked? How does Outlook access private keys? How are encrypted email, digital signature, application access, and privileged access tested? Only then comes the build. A professional build is not merely an installed operating system with policies applied. It is a controlled baseline. Hardware, BIOS, firmware, TPM, drivers, Windows version, Office version, smart card stack, certificate configuration, security policy, network behavior, and support tooling are specified as one coherent workplace product. That product must be tested before it is deployed at scale. Testing must cover the normal path and the failure path. First sign-in, smart card sign-in, PIN prompts, certificate selection, S/MIME decryption, digital signature, application access, VPN behavior, sleep and wake, docking stations, offline work, password reset, certificate renewal, device replacement, emergency access, updates, and rollback. It must also be tested with real user roles: standard users, mobile users, support staff, administrators, privileged users, and people who regularly handle encrypted communication. Professional engineering then continues in operations. Updates are introduced through controlled rings. Pilot groups are representative. Monitoring measures not only outages, but friction, repeated pin prompts, certificate errors, failed decryptions, driver failures, support tickets, rollback events, and time lost. The aim is not simply to keep devices managed. The aim is to keep people working securely, reliably, and without avoidable friction. Professional engineering is not a matter of personal taste. There are recognized disciplines for it. Quality can be described in terms such as reliability, usability, security, maintainability, compatibility, and performance efficiency. Testing can be structured, documented, and repeated. Services can be designed, transitioned, operated, monitored, and continually improved. Security and privacy controls can be selected on the basis of risk, not assumption. For a high-assurance workplace, this matters. It means that the question is not whether a solution happens to work on a good day. The question is whether the solution has been specified, tested, monitored, and improved as a critical workplace product. In government and public administration, digital sovereignty is not a side issue. Nor is it nostalgia. It means that the organization understands its dependencies. It controls critical keys, identities, and operational processes. It can assess risks. It can plan exits. It can decide where external platforms are useful and where they go too far. Modern cloud and platform services can be valuable. Intune, for example, may be an appropriate tool in certain environments, but it is not an inevitability. A modern, secure, and well-operated workplace can also be engineered in other ways. With organization-controlled PKI, sovereign endpoint management, controlled update rings, controlled driver chains, sound certificate management, tested recovery, and deliberately limited external dependencies. Giving up sovereignty too quickly may solve an operational problem in the short term, but it can create new dependencies in the long term. And new dependencies are not automatically better simply because they look more modern. Zero trust is often misunderstood. It does not mean introducing a particular product and assuming the problem is solved. Zero trust means verifying identities strongly, assessing devices, controlling access by context, protecting applications and data, monitoring events, and continuously evaluating risk. The US Federal Zero Trust strategy requires phishing-resistant, multi-factor authentication and device signals. But it does not require a loss of sovereignty, nor does it prescribe one specific product model. That distinction matters. Modern security is not the same as maximum platform dependency. Modern security is methodological. Strong identity, meaningful device assurance, clear policy, verifiable access, auditability, resilience, and controlled operations. There is, of course, a cost argument. Smart cards require infrastructure. They require cards, readers, certificate services, issuance processes, registration authority functions, support, renewal, revocation, replacement, and operational expertise. Removing these elements can reduce visible costs. But visible cost is not the same as total cost. If the organization still requires high assurance identity, strong authentication, digital signature, email decryption, privileged access, recovery, auditability, and organizational control over keys, then these functions do not disappear. They have to be provided somewhere else. The registration authority may become an identity proofing process. The certificate lifecycle may become another credential lifecycle. Smart card support may become device-bound credential support. Card replacement may become device replacement, account recovery, or emergency access. PKI operations may be reduced in one area, but retained in another for certificates, encrypted communication, application authentication, domain controller trust, or interoperability with existing systems. A serious cost case must therefore compare complete architectures, not isolated components. It must include migration cost, parallel operation, user support, re-engineering, licensing, platform dependencies, recovery procedures, audit requirements, incident risk, loss of sovereignty, and the cost of reduced workability. Only then can one say whether replacing the smart card actually saves money, or whether it merely moves cost from one line of the budget to the other. The professional question is not, can we remove an expensive component? The professional question is, can we deliver the same security, the same workability, and the same sovereignty at lower total risk and lower total cost? The real question is therefore not smart card or no smart card, nor is it Intune or no Intune, nor is it cloud or no cloud. The real question is, who owns the end-to-end chain? Who ensures that hardware, firmware, drivers, card readers, smart cards, certificates, Windows builds, Office integration, network behavior, security policies, updates, monitoring and support work together? Who measures not only technical availability but actual workability? Who understands that a problem with Outlook decryption may not be isolated in the mail client but may involve certificate discovery, key access, reader behavior, cryptographic providers, user guidance, and support processes? Who can demonstrate that a replacement mechanism solves not only sign-in, but also signature, decryption, recovery, privileged use, and auditability? Who can demonstrate that a claimed saving remains a saving once migration, risk, support, licensing, dependency, and sovereignty costs have been included? And who has the professional discipline not to attribute a platform problem too quickly to a single visible technology? There is a simple replacement logic. It asks, what is causing irritation? What looks old? What can we remove? Which product can we put in its place? Which cost line can we reduce? That logic is dangerous when it confuses symptoms with causes or visible cost with total cost. Architecture thinking works differently. It asks, what are the security requirements? Which work processes must be supported? Where do the private keys reside? Who controls the life cycle? How do recovery and emergency access work? Which dependencies are created? Which use cases must not be lost? How do we measure workability? How do we test updates? How do we audit the result? What does the complete architecture cost over its life cycle? Modernization does not necessarily mean abolition. A modern target architecture may also mean taking a strong PKI and smart card base, engineering it properly, operating it sovereignly, and complementing it with modern phishing-resistant mechanisms where they are genuinely useful. Good endpoint engineering must deliver concrete capabilities. First, stable hardware and firmware baselines. Second, controlled driver and card reader integration. Third, reliable smart card and certificate processes. Fourth, tested Windows and Office builds. Fifth, dependable encryption, digital signature, and email decryption. Sixth, clear user guidance, understandable error messages, and sensible PIN prompts. Seventh, controlled update rings with real pre-production testing. Eighth, monitoring that detects friction, not only outages. Ninth, support that identifies root causes rather than merely processing symptoms. 10th, cost models that compare complete architectures, not isolated components. And 11th, architectural decisions that consider security, workability, sovereignty, and total cost together. This is demanding. But that is precisely what engineering is for. A good digital workplace does not happen by chance. It is engineered. The smart card is not an enemy. In government and public administration, it can be a highly appropriate security anchor, especially where strong authentication, PKI, signature, decryption, and controlled key management matter. Windows Hello for Business, FIDO2, passkeys, device signals, and modern management tools can all be valuable components. But they do not automatically replace a complete PKI architecture. And they do not automatically save money unless the full architecture, the full risk picture, and the full life cycle cost are considered. Digital sovereignty does not have to be sacrificed because an existing platform is poorly operated, and a modern endpoint model does not automatically require every form of control to be outsourced to an external platform. The essential task is to bring security, usability, operations, sovereignty, and cost discipline together. Engineering notebooks to a high professional standard is not a technical detail at the edge of the organization. It protects productivity. It implements security architecture. It preserves strategic control. And it is organizational responsibility.